Inter-process communication (IPC) refers to a mechanism where the operating system allows various processes to communicate with each other, and this involves synchronizing their actions and managing shared data. There are three issues with inter-process communication. The first one is how one process can pass information to another. The second has to do with making sure two processes do not get in each other's way. For example, two processes in an airline reservation system each trying to grab the last seat on a plane for a different customer. So in ensuring that these two processes do not get in each other way is an issue that we're also going to be considering. The third concerns proper sequencing. Proper sequencing when dependencies are present. For example, if process A produces data and process B prints the data that's been produced by process A. So B has to wait until A has produced some data before starting to print. It is important to mention that all these three issues equally apply to trade. The first one, passing information, is easy for trade since they share a common address space. But the remaining two problems, that is, keeping out of each other's way and proper sequencing, applies also to trade. But as the same problem exists in both processes and trades, the same solutions also applies. Processes executing concurrently in the operating system may be either independent or cooperating processes. A process is said to be independent if it does not share data with any other processes executing in the system. And also, a process is said to be cooperating if it can affect or be affected by other processes executing in the system. That means it does share data with other processes executing in the system. So we can see from these definitions that any process that shares data with other processes is a cooperating process. There are several reasons for providing an environment that allows for process cooperation. First one is information sharing. Since several applications may be interested in the same piece of information, for instance, copying and pasting, we must provide an environment to allow concurrent access to such information. Secondly, computational speed up. If we want a particular task to run faster, we must break it into subtasks. Each of these subtasks will be executed in parallel with the others. Notice that such a speed up can be achieved only if the computer has multiple processing cores, like in the case of multi-core computers. Thirdly is modularity. We may want to construct the system in a modular fashion, dividing the system functions into separate processes or threads. So once a process needs to communicate with other processes, there is need for inter-process communication mechanism that will allow them to exchange data, that is, send data to and receive data from each other. There are two fundamental models of inter-process communication: shared memory and message passing. In the shared memory model, a region of memory that is shared by the cooperating process is established, like in the case of figure A. Processes can then exchange information by reading and writing data to the shared region. But in the case of the message passing model, communication takes place by means of messages exchanged between the communicating process. These two communication models are contrasted in the figure displayed. And both of these models are common in operating system. For example, in the case of a shared memory, it's implemented in a critical section or in a critical region. So both of these models are common in operating systems, and many systems implement both. Message passing is useful for exchanging smaller amounts of data because no conflicts need be avoided. And message passing is also easier to implement in a distributed system than shared memory. We'll look further at the problem of shared memory in the next section. Although sometimes there are systems that provide distributed shared memory. Shared memory can be faster than message passing, since message passing systems are typically implemented using system calls and thus require the more time consuming task of kernel intervention. But in the case of a shared memory system, system calls are established only to establish shared memory regions. Once shared memory is established or the critical region is established, all accesses are treated as routine memory access and no assistance from the kernel is required. Now, we consider interprocess communication in the shared memory model. The fastest form of interprocess communication provided in Unix is share memory. And there is a common block of virtual memory shared by multiple processes. So processes can read and write shared memory using the same instruction they use to read and write other portions of the virtual memory space. Interprocess communication using shared memory requires communicating processes to establish a region of shared memory. So typically, a shared memory region resides in the address space of the process creating the shared memory segment. So other processes that wish to communicate using this shared memory that has been created using this shared memory segment must attach it to their address space. And you must recall that normally the operating system tries to prevent one process from accessing another process memory. But in the situation of the shared memory requires that two or more processes agree to remove this restriction so that they can exchange information by reading and writing data in this shared region or in the shared area. The form of the data and the location are determined by these processes and are not under the operating system's control. The processes are also responsible for ensuring that they are not writing to the same location simultaneously. We'll consider that when we look at race condition later on. To illustrate the concept of compressing processes, let's consider the producer-consumer problem. The producer-consumer problem is a common paradigm for compressing processes. In this case, a producer process will produce information that is consumed by a consumer process. So one process produces, another process consumes the information that's been produced by a previous process. For example, a compiler may produce an assembly code that is consumed by an assembler. The assembler, in turn, may produce object modules that are consumed by the loader. So the producer-consumer problem also provides a useful metaphor for a client-server paradigm. In the client-server paradigm, we generally think of a server as a producer and a client as a consumer. For example, looking at the client-server paradigm, a web server produces the web content such as HTML files, images which are consumed or that is read by the client's web browser requesting the resource. So one solution to the producer-consumer problem uses share memory. To allow producer and the consumer process to run concurrently, one solution to the producer-consumer problem uses shared memory. To allow producer and consumer processes to run concurrently, we must have available a buffer of items that can be filled by the producer and emptied by the consumer. So this buffer will reside in a region of memory that is shared by both the producer and the consumer process. A producer can produce one item while the consumer is consuming another item. So, in this situation, the producer and consumer must be synchronized so that the consumer does not try to consume an item that has not yet been produced. Two types of buffer can be used: the bounded buffer and the unbounded buffer. The unbounded buffer places no practical limits on the size of the buffer. The consumer may have to wait for new items, but the producer can always produce new items. But in the case of the bounded buffer assumes a fixed buffer size. So there is a limit on the size of the buffer. In this case, the consumer must wait if the buffer is empty. And in the case of the producer also, the producer must also wait if the buffer is full. So in the case of the bounded buffer, it assumes a fixed buffer size.